Hello, Integrating Man here. Today I have a very ugly looking and challenging integral which I'd like to share with you. This integral came to mind because recently a friend of mine gave me a challenge and said he wanted to see an integral that Wolfram Alpha couldn't do. So I thought of this particular integral, which is occasionally useful in the theory of Bessel functions. And I plugged it into the free edition of Wolfram Alpha, and it indeed could not come up with an answer. And it said that the operation timed out and to purchase Wolfram Alpha Pro maybe, and then maybe that could work. But there were no promises there. Anyway, in any case, let's go ahead and see how we solve this. So with this type of problem, when we have a definite integral from 0 to 2 pi involving cosines and sines of theta, it's usually best to, or it's often best, to transform to the following contour. Let's let z equals e to the I theta. Then integrate around a contour in the complex z-plane that's a unit circle. So around this contour, z is a unit circle. Then dz is equal to e to the I theta, I d theta. This is z here. And so dz over iz is equal to d theta. Cosine of theta is going to be equal to z plus z to the minus 1 over 2. Sine of theta is going to be z minus z to the minus 1 over 2i. The integral from 0 to 2 pi will be the integral around this contour. Let's go ahead and plug all of that in to the original integral. So I then becomes the integral around c, e to the z plus z to the minus 1 over 2. I'll write cosine in terms of its complex exponentials. So that's e to the I n theta, e to the minus I, and then sine I'm going to replace as z minus z to the minus 1 over 2i, plus e to the minus I n theta, e to the I z minus z to the minus 1 over 2i, times d theta, which is dz over iz. Okay. Now we have to go ahead and simplify this. This is z to the n. This is z to the minus n. I can cancel out the I here, and I can cancel out the I here. So doing all of this and then simplifying a little bit, I get that I is equal to the integral over c, e to the z over 2, e to the z to the minus 1 over 2, z to the n, e to the minus z over 2, e to the z to the minus 1 over 2, plus z to the minus n, e to the z over 2, e to the minus z to the minus 1 over 2, dz over iz. Okay, let's first of all split that up into two integrals and rewrite it a little bit. So rewriting just a little bit, I get that I is equal to, notice this e to the z over 2 will cancel with this one, and then this e to the z to the minus 1 over 2, and this e to the z to the minus 1 over 2 will give me an e to the z to the minus 1. So I get the first integral is z to the n e to the z to the minus 1 dz over iz. The second integral, notice in this one that e to the z over 2 will multiply by this e to the z over 2 and just give me e to the z over 2, e to the z. So I get z to the minus n, e to the z, and then these e to the minus z to the minus 1 over 2 cancels with this term here. Over iz dz. I'm going to do this second integral first. This second integral is e to the z. Oh, by the way, I forgot there was there's a 1/2 here because I split up a cosine. So I need an extra 1/2 here. There. So 1/2. I'm going to bring this little I out front here. I get e to the z over z to the n plus 1, taking into account this and this. This is a fairly straightforward integral to do with residues. There is an n plus 1 order pole at z equals 0, which is included within this unit circle contour. So the result will simply be 2 pi I over 2i times the n residue at the n plus 1 order pole, which will be 1 over n factorial, the nth derivative of z to the n plus 1 times this integrand here, which will just be e to the z. And then we evaluate it at the pole. Well, the nth derivative of e to the z is just e to the z. Evaluated at 0 is going to be 1. These 2's and i's cancel, and this will just be pi over n factorial. Now there's a reason I did this integral first. Let's go ahead and take a look at this integral here. And I will scoot this up a little bit. So, this integral, remember C is a unit circle in the z-plane. I'm going to make a variable transformation now. And I will say that, that u is equal to z to the minus 1. In this case, in the complex u-plane, the circle will also be a unit circle, but the contour is now traversed backwards. Now there is no pole enclosed at u equals 0. But if I wanted to add a negative sign to the integral, I could switch the direction of the contour to minus c, and then their 0, u equals 0 would be enclosed. Anyway, let me go ahead and write out the integral. So the first integral here, written out in terms of u. By the way, du is equal to minus 1 over z squared dz. Which is u minus u squared dz. So minus du over u squared is equal to dz. That first integral then becomes 1/2 the integral over c. I'm going to put a negative sign on here and put a negative sign on the contour. So negative c in the u-plane goes in the counterclockwise direction. Z to the n becomes u to the minus n. E to the z to the minus 1 just becomes e to the u. Iz becomes u over I, my z in the denominator. And then I get a negative du over u squared for dz, so plus du over u squared. This is equal to 1 over 2I integral over this negative c in the u-plane. E to the u. I have a u to the minus n. This would be u to the minus, this would be, the exponent would be minus n plus 1 minus 2. So that would be u to the minus n plus 1 du. Notice the minus c in the u-plane, and that's probably a little awkward notation here, is the same as the unit circle traversed in the counterclockwise direction. And so this integral here is exactly the same as the first integral I did here. And so the result will be pi over n factorial. So the final result of everything is that this I here is the pi over n factorial plus this pi over n factorial, or this I is 2 pi over n factorial. All right, that's all I have for you today. If you have any comments, please put them below. If you liked the video and would like to see more, please hit the like or subscribe button. And in any case, have a good day.